Good morning, Miss. Miss, today we will speak about actually two examples of, let's say, two opposite examples of exponential function, which is lesson 7 from chapter 7 on page 455, exponential growth and decay. And after the video, we will discuss together how the graphs of the growth and the decay will be. But first, let's talk about the meaning of them and they represent which kind of problems in life. Okay, now when we are talking about increasing in, for example, number of people during or among years, or increasing or producing bacteria, or when you speak about an interest, okay, which is actually if you are dealing with the costs and bank and monies, and banks actually are talking about an interest and yearly interest. Actually here you are talking about what we call it exponential growth, in which your amount or what you have, the value you have is increasing yearly, or increasing per month, or whatever the variable of the years, or the variable of the which is the exponent actually will be. Now, since growth formula is a kind of exponential formula function, so it will take the same rule, or it will be written as the same formula for exponential function, which is y equals a times b to the power x. While a, it must be more than 0, of course, because if it's 0 we have no function, no exponential function. And b, it must be more than 1. It must be more than 1, since we are talking about exponential growth. Now, how can we deal with the problems that are talking about exponential growth? Actually, most of the times you will have, when dealing with the problems about banks and money, you will have an interest. Okay, or even when dealing in other problems, you will have a rate change during year or during months. Actually, you will add this rate change after converting from percent into decimal. You will add it to 1, because as I said, in growth, b must be always more than 1. Okay. Now, so you will take the rate as a decimal after converting from percent into decimal, and you will add it to 1, and you will call this b, or the b you have it, the growth factor. Okay. Now, but when we convert, actually, as I said, we have to convert the rate from percent into decimal before we add it to 1. But in conversion, you use the percent, okay? In problems, we will represent it as percent, but when you deal it with the problems, you have to change it from percent into decimal and then add it to 1. As they said that money always have two digits, okay, or two, and when we are talking about population, it must be in ones, not in decimals. Now, if we take this example, the population of a city is 450,000 people, increases 2.5 per years. Okay, look, 2.5% per year, and it means that they are increasing yearly by this interest or this rate. Determine what the population of the city would be after each of the following years. Now, since we are talking about population and its increase, as they say, it increases, so actually we are talking about growth, let's say exponents or exponential function. So it must be the form of, it must be y equals a times b to the power x, while a is the initial amount. When we start counting, when the beginning of the years, before we go to year 1 and year 2 and count, actually the initial number of people or the initial population for that city was 450,000. So we will write it, and then we will write p. Now, as you can see in the example, we have an interest or rate of change, which is 2.5 percent. You have to change it first into decimal. So you have to divide it by 100. So it will be 0.0 25, or we say 25 thousandths. Then you must add it to 1, because it cannot be less than 1. The factor always is more than 1. Okay, then as you can see, you will put x and x as an exponent, and you will find after 1 year, you will put instead of x1, after 2 years instead, or 3 years instead of x3, and you will find the population according to the formula. Now, yes, of course, in problems like this, we have to use calculators, because we are talking about huge numbers, okay? Or, we are talking about population during years, after 10 years. So, and we start with 450,000. So, of course, we have to use calculators. Now, in other kind of exponential functions, which is the decay, it follows the same rule: y equals a times b to the power x, but b must be 1 minus the rate that you have it in the examples, because actually b is a fraction, b is a decimal. Okay, b is written as a fraction or a decimal, so it's of course less than 1. And as I said before, it must be more than 0. And I say about it, it's the initial amount. Okay, we call b is the decay factor. When you see b written as a fraction or as a decimal, you will say about it, this is the decay factor. And you will know that your function, if you want to represent it or graph it, it will be decreasing. Okay, we know this is a decayed problem because b is always less than 1. Now, for example, a city of 140,000 has a 1% annual decrease in population, and according to death. So actually they are decreasing by 1%, okay, yearly. Determine the city's population after each of the following years. Now, how actually we will find it? We will write it in the formula: if y equals a times b to the power x, while b is 1 minus, look, 1 minus 1%, but we have to change 1% into decimal, so it will be 1 over 100, so it will be 100, okay? So then you will subtract 1 minus 100, it will be 0.99. So, the population is decreased by, or the number of, by, 99. 0.99 to the power x. Then you will substitute the number of the years and find them out. How do you know the difference between growth and decay? When you see the formulas, actually, as I said, if you have b, which is the factor that is powered, or that is raised to a power, when it's a fraction or it's a decimal, we are talking about we are talking about decay exponential function. And actually, when b is a whole number, or 1 point something, so we are talking about growth. Okay. Now, compound interest, actually, we will not solve a problem about it in the